the dying method in this section of cyclic Nucleophiles. Their fourth question involves like distributing structures with the Nucleophiles with CN in.
Which page?
So the dying packet, I think it's like
Deals over?
Deals over, yeah.
And which page?
The third section with deals over.
It's right before the reader selectivity page.
The homework section.
Homework. Homework. This is my handout from the video. Which question?
The cyclic dying's fourth question.
This one here?
Yeah.
Did we not address that in the video? What did we say about it?
You just said you can do it. That's one.
I'll let you do that one? Okay, what's the answer to that one? Answer to that one. Go over here. Answer this. Have I heard it? No reaction. Yeah, no reaction. Why no reaction? Because the diene, there is a diene there, and it's a conjugated diene, but it's stuck in the S-trans conformation. Can these two alkenes rotate and become S-cis? No, they're fixed in this ring. Yeah. That diene cannot do a Diels-Alder reaction. Okay? It's like I want to make bonds to you, but I just can't do it. And if I can't rotate, I can't. Okay? All right. No reaction. No reaction. Other questions about other things? Lab this afternoon. We'll meet downstairs. Unless you don't want to. If you're good to go, we can just begin lab. If you want to meet downstairs, we can see if there's any questions about lab. Discuss it beforehand. Okay? But we need to have questions. If not, then I'll let you proceed to lab. Okay? If you don't have questions, you're telling me that you're ready to go. And I'll give you more time and let you go. All right? Other things, mass spec. We're good to go today. Anything else? Question.
With some of these, it's in our resonance where you have like a cyclohexene and you have resonance all throughout, but there's like a carbonyl group on one end and a amide group on the other. Why does it matter whether that carbonyl is kind of diagonal to the amide or whether it's more?
You're talking about resonance, yeah?
Yes, like because it resonates all the way around and all through. So what? Because the question was which of the amino groups is going to be the most electron rich, but if there's resonance all the way around, I wasn't
No, but
sure
in that type of question, and it was in the homework, is to draw resonance structures, and you got to look at all conjugation. In some cases, the amino group along here is conjugated with something over here, and in some cases it's not. If it's conjugated, that means the electrons are going to be more moved that way.
Right.
If it's not, it's like which is not, and so the electrons are not moved that way as much. Like a garden hose. I mean, if you got 1 liter of water and you put in a garden hose that's this long, versus if you put in a garden hose that was from here across the wall,
Okay.
in which garden hose would the water be spread out more?
I see.
The longer garden hose.
Right.
The more conjugation, the more electrons are spread out, and thus there's less on one site, less on the nitrogen.
Okay.
More delocalization decreases electron density at a given site. Okay. Yes. Group lab report due when you come to lab next week. Okay, substitution reactions. Everybody good? Yeah? Okay. Leaving group ability. How about nitrogen? Can it be a leaving group? Anybody got a product down here? Any questions about tosylates? Good. Convert an OH to a tosylate, it becomes a pseudohalogen, it becomes a leaving group. Ready to go. Don't have to protonate it or anything. Tosylate is a good leaving group. We'll see tosylates again in Organic 2. We'll do mechanism for forming tosylates. A little bit different from SN1, SN2. It is a substitution. The oxygen replaces the chlorine on the tosyl. It is a substitution, but it's not SN1, SN2. Importantly, when you make the tosylate, there's no change in stereochemistry over here, right? So there's no chemistry at the carbon, and so there's no inversion or anything. But now if we do a SN2, now we're doing chemistry at the carbon, right? Kicking off, and as we know, inversion comes with, SN2 comes with inversion, like Big Mac comes with fries, right? Anybody get a product down here? Called the Herzig-Meyer reaction. Anybody get a product? Anybody? Anybody? I'm sorry, I shouldn't be asking for product, I should be asking for mechanism. Product's given, right? Okay, mechanism. Okay, sorry. Yeah, very good. Pretty straightforward. Anybody else have mechanism? Anybody else have mechanism you'd like me to look at? Pretty straightforward. Anybody else? Yeah. Anybody else, guys? Okay, this is pretty straightforward, John. Okay, we ended on looking at these mustard gases. This thing will sort of fall apart. Entropy, this thing will convert to two things. Okay, it'll break apart because it's got an internal sort of SN2. These electrons come in here and kick that off. All right, just everybody entropy. All right, bam, I separated into two. Okay, driving force there. But at least in this three-member ring with a positive charge, this thing is dang reactive. Okay, got a tetraneutral carbon with a great leaving group. Positive sulfur will leave just like positive oxygen. Okay. Also, it's very strange, so it wants to leave. You might ask, why would this form such a strange ring? Well, I told you, entropy driven. One molecule breaking into two. That's the rationale. But at this point, bam, then biomolecule, this very reactive carbon with a leaving group. Come in here and kick that off. And now your biomolecule nitrogen bonded to that carbon and then it got kicked off. Now, the nitrogen is going to have to lose an H to go neutral. If you look at the mechanism, the chloride will take the H, and that's going to form HCl, which is also bad, because then you start forming HCl in your lungs if you breathe this stuff. Not only that, you're reacting to biomolecules, so you got other toxicity. It's bad news. Okay. Some of these are actually used as for anti-cancer agents. It's kind of old because they're not that selective. But right here, this lone pair come in here and kick that off, right? And you're going to get a three-membered ring with nitrogen. and the nitrogen will be positive, analogous to this. But then you can come back and do the same type of mechanism, and you can start alkylating things. Problem is, you want to kill cancer cells and not regular cells. And so you want selectivity. And that's one of the hardest things about treating cancer. Killing the bad cells and not the good cells. And so, how selective are these things? Historically not that selective. That's why when you give them to patients, you get a lot of side effects. Lots of other bad stuff is going on, hurting the patient. So you balance, okay, is it okay to have some major side effects we know, such as loss of hair, but many other bad things? Okay. Or do we just let the patient die? So this is conflict here, okay? Can you improve the selectivity? Well, do cancer cells do things differently than normal cells? Yeah, and then you can sort of maybe focus in on what do they do differently. Maybe we can target something. The question is, how selective are these? And everything over here can maybe lead to selectivity. Maybe this carboxylic acid is very important because cancer cells, maybe, I don't know, they like to be more acidic, or maybe they don't. Or maybe they have some type of binding that really likes the carboxylic acid because cancer cells have certain biomolecules that they've started generating more. Okay. Basically, in the end, mechanism for how these things can be alkylating agents. But the broader issue with cancer is, are they going to be selective or not for cancer cells? Right? And so, ultimately, you want biomolecules in cancer cells reacting here, as opposed to normal cells. Because once you start alkylating your biomolecules like DNA or proteins, you're going to cause problems and make the cells die, potentially. Again, if it's a cancer cell, that'd be great. Not your good cells. Okay. So a very important application, it goes back to some standard chemistry we're doing. How these things become activated, and then an SN2. In the end, is it positive sulfur? Does that seem like a decent leaving group? And the answer is yes, because when it leaves, it goes back to neutral. Just like SAM is an alkylating agent. So another application. Okay, let's turn our attention to nucleophiles. We looked at leaving groups. What about the nucleophile? Okay, first thing we can say is anions are more nucleophilic than the neutral counterpart. Which is more nucleophilic? Hydroxide or water? They're both going to end up being oxygen nucleophile with an H there remaining. Okay? Which is more nucleophilic? Anion, right? More nucleophilic than that. Okay? Because the nucleophile attacks what? Carbon. It either attacks what? Remember the page from 2 months ago? How do you make nucleophile carbon bonds? Everybody needs to have that page very handy. Okay? I'm not going to give it to you again. I gave it to you 6 weeks ago. Okay? It's green, right? There you go. What are the two ways? What's the first way? Roman numeral 1. Okay, nucleophile attacking carbocation. If something attacks a plus, the nucleophile thus must be negative. Yes, nucleophiles are negative. Okay? The more negative they are, the better. Which one's a better nucleophile? The negative one. Because it's attacking a plus. Does that mean that water cannot attack a plus? It can. There's a lone pair. We've done it before. But it's not a nucleophilic S hydroxide. What's the other way to make a nucleophile carbon bond? Kicking off the leaving group. Okay? Can a nucleophile attack this? We've said this before. Okay? Why would it? That's not a carbocation. Why would a nucleophile attack there? Because it is partial plus. It's a dipole. Nucleophiles attack positive areas, either formal plus or partial plus. What type of species would attack these positive areas better? Okay. We Again, does that mean this cannot? It can, it's just not as good. Anything with a lone pair can theoretically be a nucleophile. Which is better nucleophile over here? Of course, the anion. But again, you see, you can have the neutral nucleophile. It can be the neutral version, or it can be the anion version. Not always, but in these two cases, it certainly could be anion or neutral. Okay? And I see some students are like, well, Dr. Stevens said that's a good nucleophile, so this is not. No, I never said that. That's actually a pretty good nucleophile, too. Pretty good base, too. But that's a better nucleophile and a better base. Okay? What about other examples? Let's go to different atom types. Which is more nucleophilic, ammonia or water? They're both neutral. So we're going to have to look at something else. Which one's more nucleophilic?
Water,
Why is it water?
because it has more electron density, so it's going to want more positive.
I don't know if I can argue with more electron density. You're saying because it has two lone pairs and not one?
Yes,
Yeah. I don't know how to come back to that, but that's not the answer.
it's more electronegative.
It's reasonable. There you go. It's more electronegative. Okay? Obviously, it's more electronegative. Is that going to make it a better nucleophile? Is that going to make it more willing to attack here? Okay? Or this? These are two things you can attack per the, what sheet was it? Green sheet? From 6 weeks ago? 2 months ago? Okay? Which one's going to attack these sites better? Easier? Oxygen's more electronegative. Is that going to make it more willing to come in here and... No. Oxygen holds it tighter. It's like someone who... Let's talk money. That money's got to come in here and be kind of pushed in here. Who's going to give money more? Someone who holds the money kind of tightwad? Or someone who's kind of free with their money? Nitrogen's more free with the electrons. Oxygen holds them tight. Nitrogen doesn't hold the lone pairs tight. It lets its lone pairs get out there and do backside attack and stuff. Okay? Not as good of a parent. Okay? Ammonia. Same thing. It's the same argument with basicity. Which is a better base, ammonia or water? Ammonia. Because when you start talking about base, you're not attacking one of these. What are you attacking? You attack H+, you call it a base. When you attack these, you call it a... What do you call something that attacks these? Nucleophile. Yes. I underlined it in G up there. Is that the first time we've defined nucleophile? It actually might be. Because I don't like to define things early on. I like to arrive to a... Everybody good what a nucleophile is? We've been using them for a while now. Go back and look at all your nucleophilic additions to carbocations. Okay? Which is more nucleophilic, H2S or water? Well, the answer's here. Why is H2S more nucleophilic?
Atomic radius is larger and
Oxygen's better parent. Tighter. Sulfur, they're more out there. Less electronegative. And they're just more out there because sulfur is in a lower down row. Yeah? So the electrons are further out there just because of bigger outer shell. Yeah. Sulfur is actually a pretty good nucleophile even though it's neutral. And your body uses sulfur as nucleophile a good bit. Pretty good nucleophile, pretty lousy nucleophile. We'll sum that up a little bit later when we talk about, okay, which ones are strong or what. Right now we're doing relative. Which is a better nucleophile, I minus or F minus? Of course, there's 4 lone pairs on each of these, right? I minus is a better nucleophile. Which is a better leaving group, I or F?
I.
Yes. The bigger halogen is both a better leaving group, but also better nucleophile.
F is a bad leaving group and bad nucleophile. What do we know about F? It holds the electrons super tight. It's a very good parent. It doesn't let those kids get out there and do backside attack and stuff. Okay? Won't even let them out in the house. Okay? All right? I'm holding you tight. I'm very strict. All right? Hydrogen is like, whee, backside attack. All right? Don't let your kids get out there and be doing backside attack. Got to protect the electrons. Okay, there were some things there. I would probably read what was in bold. I'm not sure I clearly read it to you, but you can read it. Next thing, steric effects. Can sterics affect nucleophile ability? Yes, look at these amines. They're all decent. Well, a neutral nitrogen is a decent nucleophile. Depends on hybridization. Just like with bases. All these amines are sp3. The lone pair is sp3 orbital. Primary means more nucleophilic than that one in this one. Tertiary mean. Why?
Electron density.
Less sterics. Okay? We talked about, okay, if we're maybe attacking this here, and the nucleophile wants to kind of get in here, it's like, I can't get in there. Okay, because remember, there's H's here, right? I'm blocked. Forget it. And we talked about sterics being around the thing with the leaving group. But what about sterics around the thing with the nucleophile? I mean, that's a primary halide. There's not a lot of sterics there. But what if your nitrogen has lots of sterics around it? You know, this thing tries to approach, and this group is going to start interacting here. You know, it'd be like, I can't get in there. Basically, sterics is important with both your electrophile, the thing with the leaving group, but also the nucleophile. Okay? It's like an airplane trying to pull into a hangar. It's going to come in there and it's like, oh, the wings are going to get... What can pull into a hangar better, an airplane or a blimp with no wings? A blimp with no wings can sort of go in there. You put wings on the airplane, it's going to be like hitting the doors and things. All right? Sterics. In fact, this is a pretty poor nucleophile. It's often used as a non-nucleophile base. We'll talk about that more, and I'll refer you back to this comment right here. Tertiary amines are considered non-nucleophilic because they're so sterically congested. Got these wings on them that keep them from being able to get backside. Now here the groups are on the nucleophilic atom. What about next door? In the examples below, the nucleophilic atom is the oxygen. And here we got anions, okay? And every oxygen just has one group. But look at the group, the carbon group. We start getting substitution over here. Does that matter? Yes, it still does. Maybe not as much as the above, but it still is around the nucleophile. Because again, there's H's here. And butoxide here, tertiary butoxide, is often used as a non-nucleophilic base for E2 elimination, which would be our next handout. And I'll refer you back to those two comments. So sterics affects nucleophilic ability. We've already said this. If something attacks an H, that something's called a what? Base. If something attacks anything else, it's called a nucleophile. Okay? resonance effects. You'll never be able to get away from resonance, okay? Resonance will always be a factor as you move forward in many things. Which is a better nucleophile, this oxygen or that one? Well, the answer is given. Why is this one worse?
More resonance.
Is this really a full anion on oxygen? No, we know because of resonance, that's a fake structure. The real structure is what? I think we've already probably drawn that. Isn't this really the structure here? So is this really a full minus or is it a partial minus? Partial. Which is going to attack these guys better? A full minus or a partial? Full minus. There's no resonance here. You cannot delocalize this charge. Same thing over here. Which is a better nucleophile? Okay? This lone pair is conjugated. And thus the lone pairs delocalize and spread into the ring. The nitrogen on the left is not conjugated. All the electron density is sitting on nitrogen. Higher electron density is going to attack these things better. Hybridization effect, which is better nucleophile. Obviously this one, right? Why? This lone pair is in what type of orbital? sp3, this one is in sp2. Both are nitrogens. There's no resonance involved with either. What's the difference? Hybridization. Comes down to a better parent. Which nitrogen's a better parent? Which nitrogen holds the electrons tighter?
sp2.
Yes. More S character. More S character, electrons held tighter. So this comes down to just hybridization. Okay? Hybridization. Okay, you can rank those on your own. Summing it up, what type of nucleophile can participate in an SN2 reaction? I don't know if that's really a summary. It's sort of a, let's give a take-home statement, and the take-home answer is right here. Only strong ones. Because, let me ask you this as we leave. Is a nucleophile involved in the rate-determining step of an SN2? So be real quick with that. Good. If you're not, you need to make sure you know what your rate-determining steps are. Since it's involved in the rate-determining step, which is the hard step, the slow step, the nucleophile needs to be good. It needs to be strong. If it's weak, it ain't going to be able to do that hard rate-determining step. Okay? The question, though, is which ones are strong? We've compared one to another, but maybe neither one of those are actually strong. That was relative. This becomes more absolute. We'll pick up here. Please be reading. You've got to be able to identify strong nucleophiles versus weak nucleophiles.
Oh no, who's writing that?
Oh man.
How much they give us? It's just, they give us like maybe 7. Because I haven't done. Or the TDL's on? No. That's what I'm doing. It'll be fine. Yeah. It's not that bad. You can do it. We're working in groups today, right?